Daniel Demmler, and he'll be talking about privacy-preserving interdomain routing at internet scale.
All right, here we go. Good morning, everyone. Thanks for showing up so early. In case you're here for the anonymous communication session, you're in the right room. In case you want to go to the MPC session, you can just stay because this talk will also contain MPC. So yeah, welcome. My name's Daniel. This is joint work with a lot of guys from Cornell Tech, University of Jerusalem, TU Darmstadt, and the University of California in Berkeley. So before I start with the topic, a short disclaimer. I was in charge for the privacy-preserving part of this work. So in case you know something about interdomain routing, you probably know more about BGP than I do. So please excuse me if the terminology is not 100% on spot. But my co-authors reassured me that everything what we did should work out. So yeah, I have no idea what I'm doing. What is BGP? Like the layman's explanation of what I understand about is you have a network, nodes are connected, and you want to add something to it. And what you want to find out is how to get to this node that got added to the network, or something in the topology changed. So you want to figure out routes to a new node or routes to a node where the topology has changed. Compute all the routes. There's a problem with it, namely convergence. So that means since BGP is decentralized, it takes in the order of minutes until these routes are computed. Sometimes there are loops and routes toggle back and forth. And also there's privacy issues. So there are works that have figured out that you can determine information about, you can determine something about confidential business information by just looking at how these routes are computed. So these are issues that we try to solve by basically centralizing everything to some extent and then throwing SMPC on it in order to solve the privacy issues that arise with that solution. The idea is not entirely new. There has been work like 5 years ago. The problem is that this work did not really scale back then. They only considered the toy example with a handful of nodes, and the runtimes were in the order of seconds already. So scaling this to an actually practical size is what we tried to do, and I think we achieved in this work. So I guess we can say that this is a real-world application of secure multi-party computation. We did this even at internet scale, which means we looked at 56,000 autonomous systems with more than 230,000 connections between them. And we offer two solutions that protect either the relations between the nodes, meaning if a node is a provider or a customer, so who's paying whom, or if they have a peering relationship. Or the second solution that we offer is that we can protect the export policies of the nodes. And more specifically, we can also hide, nodes can specify preferences that they have for other nodes, and we can protect this information. So we don't know the more fine granular relation between the nodes, not just if it's a customer or provider relationship, but also the preferences that they have between them. The technique that we use to solve this problem is secure two-party computation, which dates back to the 80s. So it's basically ancient in terms of IT systems, but not so ancient in terms of cryptography. But it took a while to take off and to become practical. The nice thing about it is everything that is efficiently computable can be turned into a secure or a private version by using secure two-party or secure multi-party computation. In this case, we restrict ourselves to two parties simply because it's much more efficient than scaling this to n parties. And I have to say that this is only secure against semi-honest adversaries, but there exist solutions to basically simply turn it into a maliciously secure protocol by adding a little bit of overhead to it. So this is more of a proof of concept than an actual solution that you would want in practice, depending on your trust model as well. How this works, really briefly, is you have two parties. They put their private inputs into SMPC, and then they can basically compute any function that they want. And then they receive an output without learning about the other party's private input. This is the very high-level idea that I can tell you about it without going into too much detail. OK, how do we actually build the system in order to achieve privacy-preserving interdomain routing? As I said before, we have a centralized approach where we have these two computational nodes in the middle. Those are the MPC parties. So it's kind of an outsourcing paradigm that we follow where all of the nodes, so all of the autonomous systems, secret share their inputs. So that means their relationships or their preferences, depending on the approach, to these two computational nodes. They do the computation, which is really heavy. So the bold arrow in the middle actually is the SMPC part, which takes in the order of seconds. And these thin lines are just a few bytes where the inputs are sent and the outputs are received. Yeah, exactly. So the first algorithm that we offer is this relationship-based routing, where, as I said before, nodes can be either customers and providers, so one's paying the other to route their traffic, or they can have a peering relationship where they essentially agreed upon routing their traffic for free between the two of them. So this is not routing in the sense of finding the shortest path in the network, but instead it's economically driven. So what you want to optimize is the amount of money that you pay by routing traffic or the amount of money that you receive by acting as a provider to other nodes. So the very high-level description of this algorithm is you get as input the topology. So this is assumed to be public, so you know which node is connected to which other nodes. And you get this target AS that was the one that I showed you before that got added to the topology, to the network. But what is private, so what the computational nodes don't know are the relations between the nodes. Then you do 10 iterations for customers in order to propagate the new node to the nodes that can reach it through one of their customers. You do 1 iteration for peers, 10 iterations for providers. And as a private output, every autonomous system gets the next hop to the target. I'll show you an example right now. This is the notation that we'll be using. So providers are on top, customers are on the bottom. There's a directed edge for who's providing the service. And the peers are on one level, like horizontally, because they don't pay each other, so they are equally likely. This is just for visualizing the relations between them. This is the same network that I showed you before, some connections between the nodes. And node number 16 is added to the network. So now all other nodes want to find out how they can reach node number 16 in the most efficient, economically efficient way. So the first step of the algorithm is the nodes that can reach 16 through their customers, or if 16 is a direct customer. So first 9 gets added, then 3 and 4, and then 1 and 0. And we would do that 7 more iterations, but in this case, there are no more nodes that can be added through customer relations. The next step are the peers that get added. So node 2 and 8 can reach it through a peering relationship. And then basically all the other nodes are added that can reach 16 through one of their providers. So they actually have to pay money to route traffic to 16. We can do this, as I said, with secure multi-party computation. So none of the computational nodes learns about these relationships while computing the best route to 16. The other algorithm that we also implemented is this preference-based routing scheme, where we don't only have this sort of binary relationships. You're either a customer or provider, or you're a peer, but you can have a preference, which is like a n-bit value. I think in our experiments we use like 4 bits because we assume this is expressive enough to cover everything. And you can describe how much basically you like your neighboring ASs, and by that you can also capture this peer or provider relationship by just giving a very low preference to providers because you want to avoid paying money to them if you can take a route that goes through a customer, right? The algorithm description is a bit simpler because we don't have to distinguish between the relations. We just, for every iteration, try to find a neighbor that can already reach the target, and then we just try to minimize the one with, or we try to maximize the one with the highest preference that we have. And we determined that, as in the example before, 21 iterations is enough for every AS to reach any other AS on the network. So these numbers, we verified them on the data sets that we had, and that should work out in practice. The output is the same as before. Every node gets the next hop in order to reach the target node. In order to make this thing fly, and in order to achieve practical runtime, we had to build a Boolean circuit, which is the way to go if you want to implement things with SMPC these days. Some technicalities on how we achieve that. The main trick are basically SIMD operations, which means you do one operation on multiple bits in parallel. It's a trick that comes from CPUs, and you can sort of apply that to SMPC as well, and you save a lot of pre-processing. And also we applied a lot of parallelism on a circuit level, which is not the same as parallelism in your CPU, but in the way how you design this Boolean circuit. One very important thing that we needed to use are efficient multiplexers, because we use those all over the circuit, because we heavily distinguish between taking one way or the other. And building everything as a tree is also part of how we achieve these practical runtimes. Another optimization on top is that we ignored stub nodes. Stub nodes are nodes that don't have any customers. So we can just assume that those receive these next hop information by their providers. So we can leave them out of the computation because there is no room for optimization by computing a road anyway. Some numbers that we extracted from the KIDA data set, which is an amazing collection of information on the autonomous systems on the internet since 1998. And as you can see, the number of ASs, which is the top left graph, is basically linearly growing, except for this tiny bump up there. The number of edges is what you can expect, growing exponentially or quadratically. Looks like Bitcoin. And what's also important for our runtime is the maximum degree. This means that the node that has the highest number of neighbors that are connected to it, because we have to sort of mask this fact. So this determines a big part of our runtime, actually, and this is also growing. To give you some numbers, and these are taken straight from the paper, if you look at the brown graph on the right, I think that's the most interesting one. This is the preference-based algorithm that I explained to you. Without stub nodes, and for the most recent topology that we benchmarked, we're in the order of, let's say, 10 seconds to compute the next stop for all the nodes on this network to adding one node. The right thing is the online phase. I should say that this is the phase that you actually need to compute. The setup runtimes can be pre-computed, and you just store them on a disk. And essentially, you can forget about it because this is just number crunching that you do overnight in a server that's in the corner somewhere. The critical time is actually the online phase. So this is in the order of 10 seconds, and this is just too damn high. So what can we do about that? Well, we apply it on a more local scale. We thought that applying this on a regional level where we use RIRs, these are regional internet registries, I believe, this just minimizes the number of nodes that you look at, and by that you automatically achieve a much better runtime. And if you look at the times that I depict here, the online phase, let's say for ARIN, which is the North American internet registrar, is in the order of less than a second for the same thing. So this preference-based algorithm without looking at the stub nodes. And we would consider this a practical runtime for what we are trying to achieve. And then you just need to figure out or do the same thing at the borders between two networks and translate this at the nodes. With this, I think I'm already at the end of the talk. We have some open questions. So we were thinking about what could we do in order to, so right now we're assuming the topology to be public, but what could we do to actually hide the topology of the network to some extent? I mean, this is sort of public knowledge on the one hand, but maybe you have parts of the network where you don't want to know, don't want anyone else to know the topology. So we were thinking about how we could achieve hiding it. But the solutions that we had were far too complex in order to achieve practical runtimes. You could do this on a very local scale. Maybe that would work, but we haven't really figured out an efficient way of doing that. And also, actual deploying this is, of course, not exactly trivial because you need to break how the internet works today, and people are really reluctant to even tweak it a little bit. So we're aware that this is not exactly easy to get to fly in practice, but if you have ideas on how we could achieve that, we would be happy to talk about that. And to sum everything up, we believe this is a real-world application of secure multi-party computation, and we put in a lot of work into the algorithms and into actually implementing them in order to make this thing sort of fly. Yeah. And with that, I'd like to thank you for your attention. And in case you have any questions, I'm here.